Picture this. You're standing at a train station, watching the 315 Express blow past at 60 miles per hour. You throw a baseball forward at 60 miles per hour from the platform. Simple physics says that ball is now moving at 120 miles per hour relative to the ground, right? Velocity's add. That's how the universe works. Now let's try something different. You're on a spaceship, traveling at half the speed of light. That's 93,000 miles per second. You fire a laser forward. Question: how fast is that light moving relative to a stationary observer? If you said 1.5 times the speed of light, congratulations, you just broke physics. The actual answer? The light is still moving at exactly 186,282 miles per second. The speed of light. No more, no less. Welcome to the most frustrating, mind-bending, and universe-defining rule in all of physics. The cosmic speed limit. Light speed isn't just fast, it's the maximum velocity anything with mass can approach. Ever. Period. End of story. And here's where it gets weird. This isn't a suggestion. It's not an engineering challenge we haven't solved yet. It's woven into the fabric of reality itself. Break this rule, and you don't just travel faster. You break causality. You shatter time. You turn the universe inside out. Today, we're diving into why light speed is the ultimate prison wall, the paradoxes that emerge when you approach it, and what happens if we found a way around it. Spoiler alert, the universe has built-in defenses that make Fort Knox look like a lemonade stand. This is why light speed is the limit, the paradox that imprisons humanity. Buckle up. We're about to travel at 99.9%, the speed of light, through the strangest corners of physics. And trust me, at these speeds, things get weird. The year is 1905. A 26-year-old patent clerk in Bern, Switzerland, the guy who couldn't even get a university teaching job, publishes a paper that will fundamentally change humanity's understanding of reality. His name? Albert Einstein. The paper? On the electrodynamics of moving bodies. The impact? He just proved that the universe has a maximum speed limit, and we've been living in a cosmic prison ever since. But let's back up. Because Einstein didn't wake up one morning and decide to ruin everyone's sci-fi dreams. He was solving a genuine crisis in physics. Two theories that worked perfectly in their own domains were giving contradictory results when put together. On one side, you had Newton's mechanics. Objects in motion, forces, acceleration. All the stuff that works beautifully for everything from cannonballs to planets. Newton's universe had no speed limit. Go fast enough, add enough energy, and you could theoretically accelerate forever. On the other side, you had Maxwell's equations, the mathematical description of electricity and magnetism. And buried in those equations was something peculiar, a constant that predicted the exact speed of electromagnetic waves, light waves. That constant was 299,792,458 meters per second, or about 186,282 miles per second. Here's where it got strange. Maxwell's equations didn't say light travels at this speed relative to its source, or relative to some universal reference frame. They just said light travels at this speed. Period. Full stop. This created an absurd problem. According to Newton, if you in a car going 60 miles per hour and you throw a ball forward at 60 miles per hour, someone watching from the sidewalk sees that ball moving at 120 miles per hour. Velocity's add. It's common sense. But Maxwell's equations suggested that if you in a spaceship going half the speed of light and you shine a flashlight forward, someone stationary should still measure that light at the speed of light, not 1.5 times the speed of light, just the speed of light. That's insane. It violates everything we know about motion. It's like saying if you running at 10 miles per hour and you throw a ball forward at 10 miles per hour, the ball doesn't move any faster than 10 miles per hour, no matter who's watching. Scientists were losing their minds over this. Some proposed there must be an invisible medium, the luminiferous ether, that filled all of space, and light was a wave moving through this medium, like sound through air. In 1887, two guys named Michelson and Morley set up an incredibly precise experiment to detect Earth's motion through this ether. The logic was simple. If Earth is moving through the ether, light should travel slightly faster in one direction than another, like a swimmer going with or against a current. They found nothing. Zero. Nada. Light moved at the exact same speed in every direction, regardless of Earth's motion. The ether apparently didn't exist. Scientists started proposing increasingly desperate explanations. Maybe objects physically contract when moving through the ether, perfectly compensating for the speed difference. Maybe time itself runs differently, depending on your motion through the ether. And that's when Einstein walked in and said, essentially, what if you're all overthinking this? What if the speed of light is just constant? For everyone, always. And what if that's not a problem to solve, but a fundamental property of the universe we need to accept? This was a radical suggestion. Because if the speed of light is truly constant for all observers, regardless of their motion, then something else has to give. And that something else turned out to be space and time themselves. Einstein's special theory of relativity rested on two postulates. First, the laws of physics are the same in all inertial reference frames, meaning if you're moving at constant velocity, there's no experiment you can do to determine your absolute speed. You could be sitting still or moving at 99% the speed of light, and physics works the same. Second, the speed of light in a vacuum is constant for all observers, regardless of the motion of the light source or the observer. That second postulate is the key. It's the cosmic speed limit. And the implications are absolutely bananas. Let's say you're on a spaceship traveling at 90% the speed of light, and you fire a laser forward. You measure that light moving away from you at 186,282 miles per second. Fair enough. Now, someone standing still watches your ship pass by at 90% light speed and sees you fire that laser. According to Newton, they should see the light moving at 190% the speed of light your ship has speed, plus the laser has speed. But they don't. They also measure it at 186,282 miles per second. How is that possible? How can you and a stationary observer both measure the light at the same speed when you're moving so fast relative to each other? The answer is time dilation and length contraction. Time literally runs slower for you on that fast-moving spaceship. Your seconds are longer than the stationary observer's seconds, and the space in front of you, his compressed distances, are shorter for you than for the stationary observer. These effects precisely compensate so that you both measure light at the same speed. The universe is bending space and time to preserve the cosmic speed limit. And here's the kicker. This isn't philosophy or mathematical abstraction. We've measured this repeatedly, precisely. In 1971, physicists Joseph Haffel and Richard Keating took 4 atomic clocks on commercial airline flights, some flying east, some flying west, and compared them to atomic clocks that stayed on the ground. When they landed and compared the times, the clocks disagreed by exactly the amount predicted by relativity. The flying clocks had experienced less time than the ground clocks. We're talking nanoseconds, billionths of a second. But it was there. Measurable. Real. GPS satellites orbiting Earth at 8,700 miles per hour experience time dilation. Their clocks run slower than clocks on Earth by about 7 microseconds per day. But they also experience gravitational time dilation because they're farther from Earth's mass, which makes their clocks run faster by about 45 microseconds per day. The net effect? GPS satellite clocks run about 38 microseconds per day faster than clocks on Earth. If we didn't correct for this, GPS coordinates would drift by about 6 miles per day. Within a week, GPS would be completely useless. So when you use Google Maps to navigate, you're relying on Einstein's special and general relativity being precisely correct. The cosmic speed limit isn't some abstract concept. It's the reason you do and end up in the wrong neighborhood. But why? Why does the universe impose this limit? Why can't we just build a bigger engine, add more fuel, and go faster? Because of mass and energy, and the horrifying relationship between them that Einstein summarized in the most famous equation in physics, E equals mc. As an object accelerates closer to the speed of light, its mass effectively increases. Not its rest mass that stays constant, but its relativistic mass, the mass that resists further acceleration, goes up. At 90% the speed of light, an object's relativistic mass is about 2.3 times its rest mass. At 99% light speed, it's about 7 times. At 99.9%, it's over 22 times. At 99.99999%, you're looking at over 2,000 times the rest mass. This means that every additional bit of speed requires exponentially more energy. The closer you get to light speed, the more energy you need, and the amount approaches infinity as you approach the speed of light. Let me put this in perspective. The Parker Solar Probe, launched in 2018, is the fastest human-made object ever. At its peak, it'll reach 430,000 miles per hour, about 0.064% the speed of light. To accelerate a single grain of sand to 99.9%, the speed of light would require about 270 billion joules of energy. That's the energy released by 64 kilograms of TNT for a grain of sand. To accelerate a 150-pound human to 99.9% light speed would require about 6,000 trillion joules. That's 1,400 megatons of TNT, about 28 times the energy of the largest nuclear weapon ever tested. And that's just to get to 99.9% light speed. To reach actual light speed would require infinite energy. The universe literally won't let you do it. Light itself can travel at light speed because photons have zero rest mass. They're never at rest. They're created moving at light speed, and they die moving at light speed. Anything with mass is permanently stuck below this threshold. So Einstein didn't just discover a cosmic speed limit. He discovered that the universe has built an impenetrable barrier between us and the stars, a mathematical prison that no amount of engineering can break. The question is, why? Why would the universe impose such a harsh restriction? What breaks if we could somehow go faster? The answer is worse than you think. Because if you could exceed light speed, you wouldn't just be breaking a speed limit. You'd be shattering causality itself. You'd be creating a universe where effects can precede their causes, where paradoxes become reality, and where the concept of time loses all meaning. Let's explore that nightmare. Welcome to the funhouse. This is where relativity stops being a neat party trick and starts being genuinely disturbing. Because the closer you get to light speed, the more the universe reveals its true nature, and it's weirder than any science fiction writer ever imagined. Let's start with the most famous thought experiment in all of physics, the twin paradox. Meet Alice and Bob. They're twins, both 30 years old. Alice decides to become an astronaut and take a journey to Alpha Centauri, the nearest star system, about 4.37 light years away. She boards a spaceship capable of traveling at 99% the speed of light. From Bob's perspective on Earth, Alice's journey takes about 8.9 years, 4.45 years out, 4.45 years back. When she returns, Bob is 38.9 years old. But here's the thing. On Alice's spaceship, moving at 99% light speed, time runs slower. At that speed, time dilation means that for every year Bob experiences, Alice only experiences about 0.141 years, roughly 52 days. So while Bob ages 8.9 years, Alice only ages 1.25 years. When she steps off the spaceship, she's 31.25 years old. Bob is 38.9. Alice has traveled 8.9 years into Earth's future by moving really fast. This isn't hypothetical. This happens. Particle accelerators routinely accelerate subatomic particles to 99.9999% the speed of light. And these particles live much longer than they should. Muons created in Earth's upper atmosphere by cosmic rays should decay long before reaching the surface. But because they're traveling so fast, time dilation extends their lifespan enough to reach the ground. But the twin paradox gets stranger when you ask, why Alice and not Bob? From Alice's perspective, she could argue that she was standing still and Earth moved away from her at 99% light speed. Shouldn't Bob be the one who ages slower? This is where acceleration matters. Alice had to accelerate to reach 99% light speed and decelerate to stop. Those periods of acceleration break the symmetry. Alice's reference frame wasn't inertial the whole time she experienced forces that Bob didn't. That's why she's the one who ages less. The universe keeps meticulous track of acceleration. There's no cheating the system. Now let's talk about length contraction, because it's even more disorienting. Imagine that same spaceship traveling at 99% light speed. To a stationary observer, the spaceship appears compressed in the direction of motion. A ship that's 100 meters long when at rest would appear to be only 14.1 meters long when traveling at 99% light speed. From inside the spaceship, though, everything seems normal. The ship is still 100 meters long. Instead, space itself appears compressed. That 4.37 light-year journey to Alpha Centauri? From Alice's perspective, the distance has contracted to only 0.616 light-years. That's why she can make the trip in 1.25 years from her perspective, even though she is traveling at 99% light speed. The universe shrinks the distance to compensate for the time dilation. Space and time are trading places. Time stretches, space contracts, and the speed of light remains constant. The universe is solving a cosmic equation, and we're just variables being moved around. But here's where it gets really disturbing. Let's talk about simultaneity, or rather, the complete destruction of it. In everyday life, we think of now as a universal concept. If something happens right now on Earth, it's happening at the same moment everywhere in the universe. The concept of now is absolute. Relativity says, nope, there is no universal now. Simultaneity is relative to the observer. Here's an example. Alice is on her spaceship traveling at 99% light speed toward Alpha Centauri. Two events happen. Bob sneezes on Earth, and an alien sneezes on a planet near Alpha Centauri. If these events are timed such that light from both sneezes reaches Alice at the same moment, she would say they happened simultaneously. They happened at the same time from her reference frame. But Bob, sitting still on Earth, would say the alien sneeze happened first, followed by his own sneeze, roughly 8.74 years later. An observer moving in the opposite direction from Alice might say Bob's sneeze happened first, then the alien sneeze. Three observers, three different orderings of events, and all three are correct within their reference frames. The universe doesn't have a cosmic clock. There's no universal timeline. Every observer has their own personal timeline, and those timelines only loosely align with each other. This gets even more disturbing when you introduce causality, the concept that causes must precede effects. Let us say you're retraveling at 99.9% the speed of light, and you send a radio signal backward. That signal travels at light speed relative to you. But to a stationary observer, because of velocity addition in relativity, that signal might appear to arrive before you sent it. You've just created a situation where the effect, signal received, appears to happen before the cause, signal sent, in some reference frames. The universe avoids this paradox by forbidding faster-than-light travel. As long as nothing exceeds light speed, causality is preserved. Cause always precedes effect in all reference frames, even if the time between them varies. But if you could travel faster than light, all bets are off. Here's the most famous causality-breaking scenario, the tachyonic antitelephone. Let's say you have two spaceships, A and B, moving apart at relativistic speeds. Ship A sends a faster-than-light message to Ship B. Ship B immediately sends a faster-than-light message back to Ship A. Because of how simultaneity works at relativistic speeds, Ship A receives Ship B's response before Ship A sent the original message. Congratulations, you've just built a time machine. You can now send messages to your own past. And that opens the door to every time travel paradox ever conceived. You could send a message telling yourself not to send the message, creating a logical contradiction. The grandfather paradox, bootstrap paradoxes, the whole mess. The universe's solution? Make faster-than-light travel impossible. Problem solved. No paradoxes allowed. But there's another angle to this, and it involves one of the strangest equations in physics. E equals mc squared. Most people know this equation as energy equals mass times the speed of light squared. It's usually interpreted as mass can be converted to energy, which is true. That's how nuclear weapons and power plants work. But there's a deeper implication. As an object with mass accelerates toward light speed, its kinetic energy increases. And because E equals mc, that increasing energy manifests as increasing relativistic mass. The faster you go, the heavier you effectively become. At 90% light speed, an electron's relativistic mass is 2.3 times its rest mass. At 99%, it's 7 times. At 99.9999999%, it's over 70,000 times heavier. The Large Hadron Collider accelerates protons to 99.9999999%, the speed of light. At that speed, each proton has the kinetic energy of a flying mosquito. A single subatomic particle carries the energy of an insect. To accelerate a proton to light speed would require infinite energy. The universe has created an asymptotic barrier. You can get closer and closer, but never reach it. Now imagine trying to accelerate a spacecraft with human passengers. Let us be conservative and say the ship plus passengers weighs 100,000 kilograms, about the mass of a space shuttle. To reach 90% light speed would require roughly 900 trillion joules of energy. That's 90% of the sun's total energy output for 1 second. And that's just to reach 90%. To reach 99% would require exponentially more. The amount of energy required approaches infinity as you approach light speed. And here's the really cruel part. Even if you had that much energy, physics prevents you from applying it fast enough. Your spacecraft would disintegrate from the acceleration forces long before reaching relativistic speeds. The universe isn't just saying, you can't go faster than light. It is saying, you can't even get close without resources that don't exist and engineering that is physically impossible. It's like being in a prison cell where the bars are made of mathematical equations. You can see through them, calculate the distances to other stars, imagine what's out there. But you can't leave. The universe simply won't allow it. But here is what really keeps physicists up at night. There is evidence that the cosmic speed limit isn't just about travel. It's about information. Nothing, not matter, not energy, not information can travel faster than light. This has profound implications for the universe itself. If I flip a light switch, the electromagnetic field change propagates outward at light speed. Gravity works the same way. If the sun suddenly vanished, Earth would continue orbiting for about 8 minutes before noticing the sun was gone. The universe has a built-in communication delay. No part of the universe can instantly affect any other part. This delay is fundamental to how reality operates. And this is where quantum mechanics throws a wrench into everything. Because quantum entanglement appears to allow instantaneous correlations across any distance. Einstein called it spooky action at a distance and hated it. Two entangled particles can be separated by light years, but measuring one instantly affects the other. No signal travels between them. No information propagates at light speed. The correlation is instantaneous. Does this violate the cosmic speed limit? Can we use entanglement to send faster-than-light messages? The answer is no, and the reason is maddeningly subtle. While the correlation is instantaneous, you can't control what information that correlation conveys. You can't use entanglement to send a specific message. The information you get appears random until you compare it with the other location through normal, light-speed limited communication. It's like the universe is trolling us. Sure, you can have instantaneous correlations, but you can't use them for anything useful without slower than light communication anyway. The cosmic speed limit holds, always, in every scenario, no matter how clever you get. So we're stuck, imprisoned by the fundamental structure of spacetime. The nearest star is 4.37 light-years away, meaning even traveling at light speed, which we can't, would take over 4 years to reach it. The nearest galaxy is 2.5 million light-years away. The observable universe is 93 billion light-years across. We're ants trapped on an island, looking across an ocean we can never cross. Or are we? Because here's where things get interesting. Physicists have found potential loopholes, ways to circumvent the speed limit without technically breaking it. They're theoretical, speculative, possibly impossible, but they exist, and some of them are absolutely wild. So you're stuck below light speed. The universe has made that abundantly clear. Try to accelerate to light speed, and you need infinite energy. Your mass becomes infinite. Time stops entirely. But what if, and this is a big, what if there were ways to cheat? Not by going faster than light locally, but by bending the rules of the game itself. Welcome to the theoretical physics equivalent of prison break schemes. Some are elegant. Some are insane. All of them are frustratingly far beyond our current technology. Let's start with the oldest and most famous loophole: wormholes. A wormhole is essentially a tunnel through spacetime, connecting two distant points. Instead of traveling the long way through normal space, you take a shortcut through the tunnel. You're never moving faster than light locally. You're just reducing the distance you need to travel. Think of it like this. If you want to get from one side of a mountain to the other, you could climb over it, or you could dig a tunnel straight through. The tunnel is shorter. You haven't moved any faster. You've just changed the geometry of your path. Wormholes were first predicted by Einstein as general relativity equations in 1935. The solution was found by Albert Einstein and Nathan Rosen, so they're sometimes called Einstein-Rosen bridges. The equations say they're possible. The universe doesn't forbid them. They could, theoretically, exist. Here's the problem. They're catastrophically unstable. The moment anything, even a single photon, tries to pass through a wormhole, the gravitational effects cause the wormhole to collapse faster than light can traverse it. To keep a wormhole open, you'd need exotic matter with negative energy density. And not a little bit. We're talking about quantities of negative energy that might not exist anywhere in the universe. Some physicists have suggested using the Casimir effect, a quantum phenomenon where two metal plates placed extremely close together experience a negative energy density between them. It's real, we've measured it, and it's stupidly weak. To create a wormhole large enough for a human to pass through would require more negative energy than might exist in the entire observable universe. It's like being told you can escape prison if you can dig through the floor, but the floor is made of neutron star material, and you have a plastic spoon. Theoretically possible? Sure. Practically achievable? Not even close. But let's say you somehow solved the negative energy problem. You've built a stable wormhole connecting Earth to Alpha Centauri. Congratulations, you've also built a time machine. Here, SY. Take one end of the wormhole on a high-speed journey while the other end stays on Earth. Due to time dilation, the traveling end ages less than the stationary end. Now you have a wormhole connecting 2 points in space and 2 points in time. Step through the wormhole from Earth, and you arrive at Alpha Centauri in your past. Travel back through normal space, and you can return to Earth before you left. Grandfather paradox, here we come. You've broken causality. Some physicists argue this means wormholes can't exist or can't be used for time travel. The universe would find a way to prevent it, perhaps by having the wormhole collapse at the exact moment you try to create a time machine. Others suggest closed time-like curves paths through space-time that loop back on themselves might be consistent with physics as long as they be self-consistent. You can't change the past, but you can be part of the past in a loop. This is the Novikov's self-consistency principle. Time travel is allowed, but only if the timeline is logically consistent. Try to shoot your grandfather, and the gun jams. Try to prevent your own birth, and circumstances conspire to ensure you fail. The universe becomes a cosmic novelist, editing your story to remove plot holes. Comforting? Terrifying? Both? Let's move on to the next loophole, the Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre proposed a solution to Einstein's sealed equations that would allow faster-than-light travel without violating relativity. The trick? Don't move through space, move space itself. The Alcubierre drive works by contracting spacetime in front of your spacecraft and expanding it behind you. You're sitting in a bubble of normal spacetime, surfing on a wave of expanding and contracting space. From your perspective inside the bubble, you're not moving at all. You're stationary. But the bubble itself can move at any speed faster than light, if you want. And because you're not moving relative to the space around you, you don't experience time dilation, length contraction, or mass increase. It's brilliant. It's elegant. It's a perfect loophole, and it requires, once again, enormous amounts of negative energy. The original calculations suggested you'd need negative energy equivalent to the mass energy of Jupiter. Later refinements got it down to only the mass of a small planet worth of negative energy. Oh, and there's another problem. You can't steer the warp bubble from inside it. Because you're cut off from the rest of space-time by the warp field, you can't send signals out to control where you're going. You'd need to program your destination before activating the drive and hope nothing is in your path. Because if you hit something while traveling at 10 times the speed of light, you'd release energy that would make nuclear weapons look like firecrackers. One calculation suggests a warp drive hitting a planet at 100 times. Light speed would release energy equivalent to 250 billion megatons of TNT. That's about 5 million times the energy of the largest nuclear weapon ever tested. You wouldn't destroy the planet, you'd vaporize it and sterilize everything within a few light years with radiation. So even if you built a working warp drive, using it would be an act of potential cosmic vandalism. But wait, there's more. In 2012, physicist Harold White and NASA proposed a modified version of the Alcubierre drive that would reduce the energy requirements to only 700 kilograms of negative energy. Still impossible with current technology, but at least we're down from Jupiter mass to several aircraft carriers. NASA even created a conceptual design, the IXS Enterprise, a beautiful rendering of a spacecraft with 2 enormous rings that would generate the warp field. It looks exactly like something from Star Trek, which is appropriate since Alcubierre was inspired by Trek when he designed his equations. The project got some press attention. Physicists cautiously suggested it might be theoretically possible. The internet went wild. NASA designing faster-than-light spacecraft screamed the headlines. The reality? We're still stuck at we have equations that suggest this might work if exotic matter exists and we can manipulate it in ways we have no idea how to do stage. It's like having blueprints for a teleporter that requires magic dust as a component. So wormholes need exotic matter. Warp drives need exotic matter. Seems like exotic matter is the missing ingredient for all our faster-than-light dreams. Can we make it? Is there any way to create negative energy density? Maybe. Quantum field theory suggests vacuum fluctuations, particles popping in and out of existence, create a baseline positive energy density everywhere in space. If you could create a region with less energy than this vacuum state, you'd have negative energy. The Casimir effect does this on microscopic scales. Two metal plates placed nanometers apart exclude certain vacuum fluctuations, creating negative energy between them. We've measured the attractive force. It's real. But scaling this up to macroscopic levels, we'd need plates the size of planets held nanometers apart. And the amount of negative energy would still be laughably small compared to what you need for a wormhole or warp drive. There's another approach, quantum squeezed states of light. By manipulating light waves, you can create regions with negative energy density. But again, the amounts are tiny and fleeting, measured in billions of joules for fractions of a second. To get the negative energy needed for practical faster-than-light travel, we need to advance our understanding of quantum field theory by orders of magnitude and develop technologies that make particle accelerators look like stone tools. Okay, so wormholes and warp drives are effectively off the table for the foreseeable future. What else? Quantum tunneling. In quantum mechanics, particles have a probability of appearing on the other side of a barrier, even if they don't have enough energy to climb over it. They tunnel through. Could you quantum tunnel faster than light? Kind of, but not really. The math suggests that in some interpretations, the tunneling particle's effective velocity exceeds light speed during the tunneling process. But this isn't true faster than light travel, because no information is transmitted. It's like saying you teleported from your house to your neighbors by briefly ceasing to exist. Sure, the transit time is 0, but you can't use this to send a message faster than light. What about quantum entanglement? We talked about this earlier, but let's revisit it. Entangled particles maintain instantaneous correlations across any distance. Change one, and the other changes instantly. Except you can't control what change occurs. Measuring an entangled particle gives you a random result. Only by comparing your results with the other location, through normal, slower-than-light communication, can you extract the correlation. It's like having two magic coins that always land on opposite faces when flipped, no matter how far apart they are. Sounds useful for communication, right? Except you can't control which face your coin lands on. You flip it, hit heads or tails randomly, and only when you call your friend at light speed or slower can you verify that their coin was opposite. The information still travels at or below light speed. Entanglement doesn't help. Is there any loophole that doesn't require exotic physics or violate causality? Actually, yes. Generation ships and suspended animation. If you can't go fast, live longer. Or sleep through the journey. Generation. Ships spacecraft where multiple generations live and die during centuries-long voyages don't break any physical laws. They're just engineering challenges. With current technology, we could theoretically build a generation ship to reach nearby stars in 1,000 to 10,000 years. You wouldn't arrive during your lifetime, but your descendants would. Suspended animation or hibernation could let individuals survive the journey, cool the body to near-freezing, slow metabolism to a crawl, and wake up centuries later. We're starting to see early versions of this in medical research. Therapeutic hypothermia can preserve critical patients for hours, scaling it up to decades or centuries. That's science fiction for now, but not impossible science fiction. Nothing about it violates physics. There's also the relativistic time dilation approach. Travel at 99.999% light speed, and time slows down so much that a subjective journey of a few years could cover thousands of light years of distance. To you, the trip takes a decade. To the rest of the universe, millennia have passed. The catch? You need absolutely stupendous amounts of energy, and you can never go home. By the time you return, everyone you knew would be long dead. It's technically traveling to the distant future, Not faster than light, but the effect is similar. You reach distant locations without subjectively experiencing the time. So that's our toolkit. Wormholes that require impossible materials and might destroy causality. Warp drives that need exotic energy we can't create and would vaporize anything in their path. Generation ships that take millennia. Relativistic flights that turn you into a time traveler. None of them let us casually zip around the galaxy like Star Trek. The cosmic speed limit holds. But why? What would actually break if we could exceed light speed? Why is the universe so insistent on enforcing this limit? The answer lies in something called causality, information, and the fundamental arrow of time itself. All right, we've established that the speed of light is the limit, and that all the loopholes are either impossible or impractical with current technology. But we haven't answered the big question. Why? Why does the universe care if we go faster than light? What specifically breaks if we exceed this cosmic speed limit? The answer is more fundamental than it requires too much energy or the math doesn't work. The answer is that faster than light travel would destroy the logical structure of reality itself. Let's start with causality, the principle that causes must precede effects. In a universe where nothing can travel faster than light, causality is preserved. Every event can be categorized into three regions. Events in the past that could have caused this event, events in the future that this event could cause, and events that are too far away and too recent to have any causal connection. This creates a structure called a light cone. Imagine a cone extending upward and backward from your current location and time. Everything inside that cone could have affected your light, or information from those events had time to reach you. Everything outside the cone couldn't have affected you yet. Similarly, there's a forward light cone representing everything you could possibly affect in the future. This structure is absolute. In special relativity, while different observers disagree about the timing and duration of events, they all agree on the causal structure. If event A causes event B in one reference frame, it causes event B in all reference frames. Now introduce faster than light travel. Suddenly, you can reach outside your light cone. You can affect events that shouldn't be causally connected to you. And here's where it gets disturbing. Due to how simultaneity works in relativity, an event that is outside your light cone, but in your subjective future, might be in someone else's subjective past. Let me construct a scenario. You're on Earth. Alpha Centauri is 4.37 light years away. Someone on Alpha Centauri commits a crime. Let's say they rob a bank on January 1st, 2025, according to their local clock. Because information can't travel faster than light, you on Earth won't know about this crime until 4.37 years later around May 2029. That is normal causality. But now let's say you have a faster than light spaceship. You travel to Alpha Centauri in 1 year, arriving in January 2026 5 o'clock. Due to the way relativity handles simultaneity during high-speed travel, you might arrive before the crime happened in some reference frames. You confront the would-be criminal. I know you're going to rob the bank on January 1st, 2025. Don't do it. They look at you confused. What are you talking about? It's January 2026. I already robbed that bank a year ago. But from another observer, S-reference frames someone traveling in a different direction at relativistic speeds. The bank robbery hasn't happened yet. You've created a situation where the ordering of events depends on your motion. Now let's make it worse. You use your faster-than-light drive to return to Earth. Depending on the specifics of the relativity calculations, you might arrive before you left. You've created a closed time-like curva path through spacetime that loops back on itself. Congratulations, you've built a time machine. And with time machines come paradoxes. The grandfather paradox is the most famous. Travel back in time and prevent your own birth. If you succeed, you were never born, so you never traveled back. So you didn't prevent your birth, so you were born. So you did travel back. Infinite loop. Logical contradiction. The universe doesn't permit logical contradictions. Mathematics doesn't allow statements that are both true and false. Reality can't accommodate events that simultaneously did and didn't happen. So the universe prevents this by making faster-than-light travel impossible. The speed of light limit is a causality protection mechanism. But there's another angle to this, one that's even more fundamental: information. Physics has increasingly realized that information is the most fundamental currency of the universe. More fundamental than matter or energy. Information is the stuff reality is made of. The speed of light isn't just a speed limit for objects. It is a speed limit for information propagation. No information can travel faster than light. This has profound implications. It means the universe has a built-in communication lag. If I'm on Earth and you're on Mars, we can't have a real-time conversation. At closest approach, Mars is about 3 light minutes away. I send a message. You receive it 3 minutes later. You reply. I get your response 3 minutes after that. Our conversation has a 6-minute delay per exchange. This seems annoying, but it's actually crucial for preserving the consistency of the universe. Here's why. Information is connected to entropy and the arrow of time. The second law of thermodynamics states that entropy disorder always increases in closed systems. This gives time a direction. The past is the low entropy state. The future is the high entropy state. If information could travel faster than light, you could send messages to regions of spacetime in your past. This would allow information from the future to influence the past, potentially decreasing entropy and violating the second law. The universe can't allow that. Thermodynamics is non-negotiable. Entropy increases, always. The arrow of time points one direction. Allowing faster-than-light information transfer would shatter this. There's also the small matter of relativistic mass increase. As an object approaches light speed, its energy increases toward infinity. At light speed, it would be infinite. An object with infinite energy would have infinite gravitational pull. It would collapse into a black hole that would instantly consume the entire universe. The speed of light limit prevents objects from accumulating infinite energy. It's a built-in circuit breaker. But let's dig deeper into what happens as you approach light speed. Because the effects aren't just about mass and energy, they're about the fundamental structure of spacetime. At extreme velocities, say, 99.9999% light speed space in front of you contracts so severely that the entire observable universe would appear compressed into a tiny disk directly ahead. Behind you, space would appear stretched to infinity. The cosmic microwave, background radiation, the afterglow of the Big Bang, would be blue shifted in front of you to lethal gamma radiation, and red shifted behind you to nearly zero energy. You'd be traveling through a universe that looks nothing like the one you left. Time would essentially stop. You'd age infinitesimally, while the universe aged eons. At exactly light speed, if you could reach it, time would stop completely for you. From your perspective, the journey from the Big Bang to the heat death of the universe would happen instantaneously. Space would contract to zero distance. The entire history and geography of the universe would collapse to a single point. You'd be everywhere and nowhere simultaneously. You'd experience all of time and none of it. You de-exist in a state where the concepts of space and time have no meaning. This is why photons don't experience time. From a photon's perspective, it's created and absorbed in the same instant, regardless of how far it travels from our perspective. A photon that travels from a distant galaxy to your eye crosses billions of light years and billions of years from our frame of reference. But from its frame of reference, zero distance, zero time. The photon exists outside of time. It's a four-dimensional object stretched across space-time like a wire, experiencing its entire world line simultaneously. Matter can't exist in this state. Matter needs time to exist. It needs change, causality, sequence. At light speed, all of that vanishes. So the cosmic speed limit isn't arbitrary. It's the speed at which spacetime itself breaks down. It's the maximum rate at which causal influence can propagate. It's the speed that separates matter, which experiences time, from energy, which doesn't. Light speed is the point where the universe says, beyond here, the rules change. Space and time switch roles. Causality breaks. Reality becomes undefined. It's not a wall. It's a singularity. A point where the equations divide by zero and give nonsensical answers. And the universe is very, very careful about preventing anything from crossing that threshold. But here's the frustrating part. The cosmic speed limit also determines the observable universe. Because light has only had 13.8 billion years to travel since the Big Bang, there's a horizon beyond which we can never see. Objects more than about 46 billion light-years away, that's accounting for cosmic expansion, are forever beyond our observational reach. Their light will never reach us. We can never know what's out there. The universe could be infinite. It could contain infinite galaxies, infinite worlds, infinite civilizations. But we read trapped inside a sphere 92 billion light-years across the observable universe, and we can never see beyond it. Even if we could travel at light speed, we couldn't reach most of the universe. Cosmic expansion is accelerating, driven by dark energy. Distant galaxies are receding from us faster than light, not because they're moving through space faster than light, but because space itself is expanding. Galaxies beyond our local group are moving away from us at speeds that exceed the cosmic speed limit, not through their own motion, but because the space between us is expanding. And that's allowed space itself isn't limited to light speed. So even with infinite time and light speed travel, we're still trapped. The cosmic speed limit combines with cosmic expansion to create an ever-shrinking island of accessibility. In the far future, hundreds of billions of years from now, galaxies outside our local group will have receded beyond the cosmic horizon. Future civilizations will look at the sky and see only their own galaxy. They'll have no evidence that other galaxies ever existed. The cosmic speed limit isn't just a prison. It's a prison that's shrinking. Unless there's something we're missing. Some fundamental aspect of physics we haven't discovered yet. Because here's the thing. We've been surprised before. For all our talk about the cosmic speed limit being absolute and inviolable, there's something we need to acknowledge. Physics isn't finished. We don't have a complete theory of everything. We don't fully understand the universe. And history suggests every time we think we figured it all out, nature reveals a deeper layer that changes everything. In 1900, the physicist Lord Kelvin supposedly said, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." 5 years later, Einstein published special relativity and shattered that confidence. Before quantum mechanics, we thought we understood matter. Then we discovered that particles are also waves, and observation changes outcomes, that reality at the smallest scales is probabilistic rather than deterministic. Before dark matter and dark energy, we thought we understood the universe's composition. Then we realized normal matter, everything we can see and touch, is only 5% of the universe. The other 95% is mysterious stuff we can't see and don't understand. We're constantly being humbled by reality. So when physicists say the cosmic speed limit is absolute, they mean absolute within our current understanding of physics. That's an important qualifier. There are several areas where our knowledge has gaps, and those gaps might hide loopholes. First, the quantum gravity interface. We have quantum mechanics, which describes the very small. We have general relativity, which describes gravity and the very large. These two theories are both spectacularly successful in their domains, but they're mathematically incompatible. They make different predictions about what happens when quantum effects and strong gravity interact, like at the center of black holes or at the moment of the Big Bang. We don't have a working theory of quantum gravity. String theory, loop quantum gravity, and other candidates exist, but none are confirmed by experiment. What if the correct theory of quantum gravity reveals that spacetime isn't continuous but discrete? What if at the smallest scales, the Planck length, about 10 to 35 meters, space and time are quantized into indivisible chunks? In a quantized spacetime, the very concept of speed might break down. You can't move continuously. You jump from one quantum of space to the next. The cosmic speed limit might be a consequence of continuous spacetime. And discrete spacetime might allow different rules. This is pure speculation, but it's not impossible. Second, exotic spacetime topologies. General relativity allows for bizarre geometries, wormholes, closed time-like curves, even traversable time machines if you arrange matter in specific ways. Most of these require exotic matter or violate energy conditions, making them impossible with known physics. But our knowledge of matter and energy is incomplete. Dark energy, the mysterious force accelerating cosmic expansion, has negative pressure. It's not quite exotic matter, but it's weird. We don't know what it is or how it works. What if sufficiently advanced technology could manipulate dark energy? What if there are configurations of dark energy that stabilize wormholes or create warp fields? We're not saying this is likely. We're saying we don't know enough to rule it out. Third, higher dimensions. String theory suggests the universe has 10 or 11 dimensions, with most of them curled up in microscopic scales. What if the cosmic speed limit only applies in our familiar 3+1 spacetime dimensions? What if there are shortcuts through higher dimensions? You can't move faster than light in spacetime, but maybe you can step outside spacetime briefly and re-enter elsewhere. This sounds like science fiction, but supersymmetry, extra dimensions, and bulk spaces are legitimate areas of theoretical physics research. They might be wrong, but they're not crazy. Fourth, the holographic principle and information theory. Recent advances suggest the universe might be fundamentally informational. The holographic principle proposes that all the information in a volume of space can be encoded on the boundary of that space, like a 3D hologram encoded on a 2D surface. If the universe is fundamentally about information rather than matter and energy, what does speed limit even mean? Information in quantum systems can be instantaneously correlated via entanglement. Maybe at a deep enough level, locality and speed limits are emergent properties rather than fundamental ones. This gets into metaphysical territory. But cutting-edge physics is increasingly embracing information-theoretic approaches to reality. Fifth, we might be wrong about what's impossible. History is littered with declarations of impossibility that were later overturned. Heavier-than-air flight is impossible. Lord Kelvin, 1895. Wright brothers flew in 1903. Nuclear energy is impossible. Ernest Rutherford, 1933. Nuclear chain reaction achieved in 1942. Space travel is utter bilge. Richard van der Riel Woolley, British Astronomer Royal, 1956. Sputnik launched in 1957. The pattern is clear. Experts are often wrong about what's impossible, especially on long timescales. Now, to be fair, physicists have gotten better at distinguishing between we do and know how and the laws of physics forbid it. Perpetual motion machines, for example, are genuinely impossible because they'd violate thermodynamics. The question is whether faster-than-light travel falls into the genuinely impossible category or the impossible with known technology and physics category. Most physicists lean toward the former. The cosmic speed limit seems deeply woven into the mathematical structure of spacetime. It's not an engineering limitation. It's a fundamental constraint. And this is crucial, that assessment is based on our current theories. If those theories are incomplete or wrong in subtle ways, the picture could change. Consider this. Before 1998, physicists believed cosmic expansion was slowing down due to gravity. Then observations of distant supernovae revealed expansion is accelerating. We were fundamentally wrong about the universe's evolution. Dark energy, whatever it is, represents a gaping hole in our understanding. It's 68% of the universe's energy content, and we have no idea what it is. We're fish in an ocean, having figured out hydrodynamics and making confident declarations about the nature of water. Meanwhile, 68% of the ocean is made of something we can't see or touch and don't understand. Humility is warranted. That said, let's be realistic. Even if loopholes exist, they're likely to be incredibly difficult to exploit. The universe doesn't seem to make things easy. If wormholes are possible, they'll require technology far beyond anything we can currently imagine. If higher dimensional shortcuts exist, accessing them will probably require energies comparable to the Big Bang. If exotic matter is real, harvesting it will be nightmarishly difficult. The cosmic speed limit might not be absolute, but the practical barriers to exceeding it are enormous. So where does that leave us? Where does humanity go from here? Trapped at the bottom of a gravity well on a planet orbiting an ordinary star, unable to reach even the nearest neighboring star system in a human lifetime. Option 1. We accept the limit and work within it. Generation ships, suspended animation, relativistic travel for one-way journeys. It's slow, expensive, and difficult, but it's possible with known physics. Option 2. We focus on longevity and patience. If we can extend human lifespan or transfer consciousness to more durable substrates, centuries-long journeys become feasible. Option 3. We send proxies, self-replicating probes that explore the galaxy on our behalf, reporting back with discoveries. We experience the cosmos vicariously through our robotic representatives. Option 4. We wait. We invest in fundamental physics research, hoping future generations will discover loopholes we can't currently imagine. Maybe in 100 years, maybe in 1,000 years, someone will crack the problem. Option 5. We accept that we're staying here. Earth, the solar system, maybe a few nearby stars if we're ambitious. But most of the universe is forever out of reach, and we make peace with that. Personally, I think we'll pursue all of these simultaneously, because that's what humans do. We explore. We push boundaries. We refuse to accept limits, even when the universe tells us those limits are non-negotiable. Will we ever exceed the speed of light? Probably not, if our current physics is correct. Will we try anyway? Absolutely. Because the cosmic speed limit isn't just a scientific fact, it's a challenge. It's the universe saying, you can't, and humans have a long history of responding, watch me. Maybe we'll find a loophole. Maybe we'll invent something that bypasses the limit without technically breaking it. Maybe we'll discover that our understanding of spacetime is incomplete, and there is a deeper layer where different rules apply. Or maybe the speed of light really is absolute, and we're stuck with it. Maybe the universe is vast and lonely, with intelligent civilizations scattered across such immense distances that contact is effectively impossible. Maybe we're destined to wonder what's out there without ever knowing for certain. The cosmic speed limit is many things. It's a fundamental constant of nature. It's a consequence of space-time geometry. It's a protection mechanism that preserves causality and logic. But most of all, it's a reminder that we're small, that the universe is vast and ancient and indifferent to our ambitions. That reality operates by rules we didn't write and can't change. We can measure it, understand it, even use it. GPS satellites rely on relativistic corrections. Particle accelerators manipulate particles at 99.99999% light speed. We've made the cosmic speed limit into a practical tool, but we can't break it. Not with current physics, not with known technology, not by brute force or clever engineering. The prison bars are made of spacetime itself, and spacetime doesn't negotiate. So we have a choice: rage against the limit, or accept it and work within it. Spend our resources trying to break an unbreakable rule, or use those resources to explore what's accessible. Personally, I think there's something poetic about the cosmic speed limit. It means the universe has structure, rules, logic. It means causality is preserved, and reality is consistent. It means time flows in one direction, and effects follow causes. Without the speed of light limit, the universe would be chaos. Events affecting other events in random order. No timeline, no causality, no logic. Just a jumbled mess of occurrences with no structure. The cosmic speed limit is what makes the universe comprehensible. It's what allows science to exist. It's what permits us to understand reality in the first place. So maybe instead of cursing it, we should thank it. And then, because we're human, we should immediately start looking for loopholes anyway. Because that's what we do.